Hi, my name is Nigel Sebastian, and this is the video project task 3, and obviously this is the video project that is outlining the whole process. So basically going back from the very start, so introducing the structure. So in this case, I chose the tram stop, which is located next to Melbourne Central Station, and mainly the material it is made out of is steel. And as you can see, there are photos from various angles, and there's obviously one with me in it. So we were asked to choose a structure with one beam-like structure, and in this case, the tram stop, obviously as you can see on the top, there's a horizontal beam, and that was the beam that I mainly considered in terms of my calculations. And the length of that in this case is 6.41 meters, and the breadth is concerning that little trapezium shape on the side. As you can see from the side view, that's the breadth, which is 0.33 meters, and the height it's also shown in the side view, which is 2.5 meters. Now, going back a few pages and focusing on the second video profile task. So in this case, we were asked to draw shear force and bending moment point, bending moment. And in this case, the point load amount was to be calculated. So in my case, since the as my student number ended with 0, the max load value was 13.33 kilonewtons per moment. And obviously that multiplied by the length would give the total assumed point load. So in this case, as it was also made from steel, the value was 210 GPa. So my main structure was under group 2, the tram stop, including swings, sheds, and verandas, so that fell under that group. And obviously in my case, the max load value was 13.33. And the free body diagrams were I used with the respective sign conventions. So as you can see in the diagram, I verified the sign conventions. So the right side is positive and the upper side is positive as well. And obviously I went through some equations, and I was able to derive sigma fx, sigma fy, and sigma moment z using the simultaneous equations here. And finally, I found the moment to be 273.85. And similarly, in the second case, I applied the equilibrium equations, and just like that, I found the moment to be minus 13.33 x squared over 2. So using those, I was able to attain these diagrams. Obviously, one was the shear force diagram, which is the first one, and then the second one was the bending moment diagram. So obviously these diagrams were able to be attained from the equilibrium equations and the moment equations derived before. And as a result, I was able to find the maximum value for each of the cases. So in regards to the shear force diagram, the maximum value was found to be 85.4453. And in the second case, the bending moment diagram, the minimum value was found to be minus 273.85. So going on with this task, the next part was to determine the slope and deflection. And as you can see, these calculations were made in terms of the finding the reactions. Just like before, we had to use specific equations. In this case, the formula is outlined by this integration process. And just before, the free body diagram was also again drawn in order to outline the moment and the x value that we're finding in order to form the integral formulas for the whole process of finding the slope and deflection. EI theta and EIV is derived from that main formula of the double integration. And using those two formulas, integrating each one, I was able to find the slope at midpoint and the maximum slope. And by attaining these values, I was able to substitute into each of those formulas to find the total slope, the general formula for the slope and deflection. And once I've substituted those values, for example, for a certain length, in order to find the deflection at that specific length, in this case, the x value was taken to be 6.41. I would sub that into that slope equation. In this case, it was EI theta, and just like that, I would also substitute into the deflection formula, which is EIV, and I would get the respective values. And this would obviously be the deflection. So this would represent that the deflection at this specific length, which is 3.205 meters, in order to attain the maximum deflection. And then going on with the working out, going back, we come to the third task, which is to find the bending stress and the shear stresses, maximal principal stress, and in-plane shear stress and failure planes. In this case, the bending stress, as you can see, is going through a similar process where I drew a free body diagram, and obviously we had to use the SFD and BMD values from the task 2. So in this case, the moment max was negative 273.85 and the Vmax was 85.4453. And in this case, I had to find the moment of inertia for this composite shape. And as I've mentioned before, my cross-section of the shape was a trapezoidal shape, a trapezium, and due to that, as it is a composite shape, in order to find the IX, I had to split that into basic shape. So as you can see, 2 triangles and a rectangle, and using that, I was able to split it into 3 shapes and then find the IX for each of them and combine it all together to find the total moment of inertia. And as you can see, the formula at the end outlines the normal stress in the member, and the M represents the resultant internal moment, and the Y is signifying the perpendicular distance from the neutral axis. As you can see, the neutral axis is outlined in that free body diagram I drew, where the halfway line marks the neutral axis, and the I obviously it represents the moment of inertia. So this was the main process. And in addition to this, the shear stress was the same method where I would use Vmax and the area of the trapezoid. So the area would be the area of that rectangular shape from the halfway line. So the length would be 8.25 centimeters. Obviously, I would have to convert it to the international units. But in this case, I would have had to find the V. V was the vertical shear force. A, the partial cross-section area, so the A apostrophe represents that. The Y dash, the distance to the centroid. And the I, obviously the moment of inertia. And B, the width of the cut. And using those values, I would have had to calculate the total XY value of the shear stress. So as you can see, I attained those values from the previous equations too, and then substituted in to find the maximum value of 2.16 times 10 to the power of negative 5 ampere. And finally, this goes on to outline the maximal principal stress. Obviously, the equations were used from the lecture, and this process basically outlines that. Obviously, the 0 outlines that the vertical values wouldn't be considered. It would only work with the horizontal aspect. So as you can see, the rest of the calculations are done like that, according to the lectures as well. And similar with the in-plane shear stress, the same formulas were used in order to calculate the final Tmax. So this would be, as you can see, in plane, it would be plus or minus 2.16 times 10 to the power of negative 5 MPa. In the failure plane, as you can see, the observed angles from max principal stresses and in-plane shear stresses come down to be 0.90 degrees. So that's the angle that I found. And obviously due to this, the structure would fail at 0 degrees, resulting the probable failure plane to be at 0 degrees. And the structure would be at one angle of 45 degrees. So that's basically outlining the failure of whether the structure would fail at a specific angle. So that was basically outlining that task, and now going down to the conclusion. Obviously, these tasks were split into 3 parts, so I did get enough time to go through it. So overall, I found that to be very helpful, splitting it and focusing on each part. And so that's how the calculations were processed in accordance with the lecture. So thank you.